The mission statement was to design aspects of a scientific instrument that could be deployed on a submersible craft into the oceans of Europa. I elected to build and design a scientific camera package that would be mounted on a 5 degree of freedom robotic arm. So in order for my camera to be successful, it needs to fulfill 4 requirements that I've set for it. Number 1 is it needs to be multispectral, which means that it needs to be able to sense as much of the light spectrum as possible. In this case, it can capture visual light as well as infrared light, and then in the future, hopefully near ultraviolet as well. Secondly, it needs to be able to follow a predetermined path that I can set using the MATLAB path generator in 3D space. Thirdly, it needs to be able to have a lock-on ability of sorts where it can, no matter where it is in space, point the camera at that point so that it can properly observe it from all angles. And lastly, it needs to have 5 degrees of freedom, which will give it enough maneuverability to follow those paths. Did you get that? So the very first thing that I did for this project was to design a pathing script in MATLAB. Basically, what it does is it takes in a point of interest, which can be anything in the field from a cool-looking rock to maybe a fossil that they found or maybe a heat vent of some sort, something that you want to analyze. In this case, it's just that point on there on the graphs, the little X in the middle. Following this, you can define 3 functions, one for the x-coordinate, one for the y-coordinate, one for the z-coordinate, that you want the camera to follow. So in this case, it's the red path there on the graphs. What will happen is the MATLAB script will determine how to position the following link, which will be the second link of the robot, how it can position that link so that the camera is always pointing at that point of interest. This is really, really good because it allows you, in the case of the orbital one there, you see where it spirals around. This is really effective because you can get all angles of the point of interest. So this is a quick circuit diagram of my robot here. In the middle, we've got the control and testing system, which includes the Arduino and the potentiometer. On the left-hand side, we have the servo controller system, which includes the servos and a 6-volt power supply and the servo controller. In the very bottom there, we have the camera module system, which includes the visual camera and the near-infrared sensor. And up on the right side in blue, we have the stepper motor system, which includes the H-bridge motor driver and the 12-volt power supply as well. So just to give a quick overview of the robot itself, up at the top, we've got our infrared camera and our visual camera. This one is a slower frame rate, where this one is a higher frame rate and a higher resolution as well. Right behind them, we've got our 4th servo motor, which handles theta 4 as its input angle. Right next to that, we've got the wrist motor, which is theta 3. If we keep going down the line, we've got theta 2, which is the elbow motor. All the way down at the bottom here, we have theta 1, which is dealt with by this servo motor here, and that's like the shoulder of the arm. That is bracketed into the lid here, which underneath is the stepper motor that rotates the whole base. If you can see it in there, it's screwed in through here, through this hole. So in this footage here, you can see a quick demo. The camera footage on the right is what's coming out of the camera on the robot, and you can see that as it moves up and down, it does follow that wrench there and battery pack. It is quite unstable, so that's probably what I'd be changing next time around.